atmospheric Cherenkov technique, EACT, to perform indirect observations from the ground. We basically, when gamma ray photons interact with the Earth atmosphere, they produce via pair production electrons and positrons and secondary gamma rays, producing the electromagnetic cascades. These particles, electrons and positrons in the cascades, move faster than the speed of the light in the Earth atmosphere, producing Cherenkov flashes lasting a few nanoseconds and peaking in the UV blue wavelength range. And the Cherenkov telescopes collect these Cherenkov flashes, reflect them in the cameras in the Cherenkov mounted on the telescopes, that allow us to study the Cherenkov flashes images in the camera plane and inferring information about the primary gamma ray emission. The problem of this technique is that cosmic ray particles continuously hit the Earth atmosphere, producing in a similar process different products, producing the so-called hadronic cascades that also contain the particles moving faster than the speed of the light, and so producing Cherenkov light. Indeed, cosmic ray particles are the main source of background for EACT. We have one gamma ray event every 10 to the 4 events, but luckily these two kinds of events look differently in the camera plane, so we can distinguish between them. And this is one of the main aim of the EACT analysis, indeed, the separation between gamma ray and proton origin of the event that we collect in the during the observations. And we can do that by parametrizing the Cherenkov images in the camera plane and distinguishing the two kind of events on the basis of these parameters. Once we have the list of the gamma ray events, the signals, we can do the astrophysical analysis of our sources. We can study the observables, the energy and the direction of these sources. We measure the energy because the energy of the primary gamma ray photon is proportional to the Cherenkov, the density of Cherenkov light that we collect in the camera, in the telescope cameras. And we measure the direction through axis intersection when we do the observations with multiple telescopes, so using a stereoscopic mode. Something that is also important for very high energy observations are the theta square plots. That is something that you usually find in very high energy papers, mainly when they claim a new detection, you will find something like this. In the theta square plot, we put the number of events, both the signal represented by these crosses, these black crosses, and the background represented by these colored areas. And these events are plotted against the theta square parameter, that is the distance between the reconstructed source position, the one that we get from our analysis, and the true source position in the sky. So when we have no detection, both the signal and the background are randomly distributed, while for when we have a detection, we have that most of the signal is close to the true source position. So the most important EACT experiments operating right now on Earth are the Veritas telescopes in Arizona, USA, the two MAGIC telescopes in La Palma, Canary Islands, and 5 telescopes in the S system in Africa. But the next generation of EACT experiment will be represented by the CTIO, the Cherenkov Telescope Array Observatory, that will be made of about 60 telescopes of different sizes, optimized for different energy ranges, and located in 2 different sites, the CTIO South in Chile and this north site in La Palma, close to the MAGIC telescopes. Here in Bologna, we are hosting the headquarters of the CTIO. So let's move on introduction on blazars. These objects are a subclass of active galactic nuclei in which the accretion flow onto a supermassive black hole lead to the production of relativistic outflows that in the case of blazars are aligned to the line of sight of the observer. And due to this geometrical configuration and the relativistic speeds, we have that the emission is boosted in the direction of the observer, and they overshine the emission of the host of the nuclear region of the nuclear region of the host galaxy. In most of the cases, we have non-thermal emission from the jet, from radio up to very high energies. And this is an example for Markarian 421, that is one of the most studied blazars known. In this spectral energy distribution, you can also recognize the typical two-component shape of blazar SED, for which we have an explanation for the low energy component, that is synchrotron emission from a population of electrons moving in a magnetic field. While for the high energy peak, there is still an open debate. There are multiple scenarios. According to leptonic scenario, is a population of electrons interacting with a photon field, leading to the high energy emission via inverse Compton interactions. And if the photon field is coming from the jet itself, we talk about synchrotron self-Compton scenario. Otherwise, if the photon field is from regions that are external to the jet, as the broadline region or the dusty torus, we talk about external Compton scenario. According to hadronic scenarios, instead, there is a population of protons that are contributing to the emission of the high energy via proton synchrotron or proton photon interactions. Regarding this last emission mechanism, these are really interesting in the multi-messenger context, because one of the products of these interactions, so the interactions between protons and photons, are not only the high energy emission that we observe in blazar SED, but also TV to PV high energy neutrinos. So this makes blazars a good candidate as neutrino sources. Okay, we study blazars emission mechanism through observations and through SED modeling. The simplest approach to do this is to assume a one-zone model in which the emission is coming from a blob that is filled with homogeneous magnetic fields and with particles that follow a particle distribution. The problem with this approach is that we have a high number of free parameters, as the ones describing the emission region, that are the size of the region, the magnetic field, the Doppler factor, the viewing angle of the region. And also we have the parameters describing the particle energy distribution. In the case of an hadronic model, we have only the parameters describing the electron energy distribution, but in hadronic models we have also the proton energy distribution. Okay, so really complex scenario where we have high number of parameters and high degeneracy between them. But we can complicate the situation even more by assuming different emitting regions with different physical characteristics, as for example, different particle distribution, different magnetic fields. For example, here I'm showing you two blobs located at different distances from the central black hole, and each of them contributes to the observed spectra depending on these on the physical condition in these regions. They can interact between each other, so we increase the complexity of the system because this allows us to to explain why we observe different variability timescales at different energy bands and why we observe some intra-band correlation patterns. From a VLBI point of view, we have high angular resolution, so we can study blazars in their parsec scale regions. One of the most powerful tools that we have to study blazars with VLBI is to model our data with Gaussian components that identify bright knots in the jets that can be both moving knots or stationary knots. And by the study of the evolution of these components, we can measure different parameters. I have no time to go in detail on how we use the study of the components to retrieve all these parameters. But we have to keep in mind that the motion of the components are also affected by the relativistic velocity and the small viewing angle that lead us to observe high Doppler factors. And this means boosted emission. And by studying, by observing the sources with certain time intervals, we also observe apparent superluminal motions that are due to these relativistic effects. Basically, we measure the distance between two components at different epochs, measuring the proper motion of the velocity with which these components moved. And from this, we measure superluminal motions, but we also can get information about the Lorentz factor and the viewing angle. And what we found from this, for the measurement of these parameters, is that sometimes these are in disagreement with what we observe from very high energy observations and from the SED modeling. These lead to the so-called Doppler crisis that can be solved by assuming that very high energy and VLBI radiation are coming from different regions in the jet. We can also measure polarization in VLBI at VLBI scales. Something interesting that was found in Blazar polarization image is that the polarization direction can change from different layers in the jet. As for example, in this source, we have the inner and the outer jet show different perpendicular polarization directions. This can be explained by the presence of velocity structure. That is something that we can infer even from limb brightening. That is a feature that we found in several blazars, in which the edges of the jet are brighter than the central part. Again, meaning, or one of the explanation is that we are observing layers with different velocities, moving at different velocities, producing this effect. All these information are crucial to set the models for the SED modeling, so we can break the degeneracy between all the parameters that we have in the SED modeling. And for this reason, the VLBI observations are very important for the study of blazars. From a VLBI point of view, we study blazars using light curves, flux versus time, and energy distribution. But what about imaging with very high energy observations? We are from radio VLBI point of view, we are used to very nice images where we can do measurements on the parameters of from the parameters of the image. This is the nice example of M87 for which we have kiloparsec scale observations up to EHT observations that allow us to especially resolve the source very well, but with very high energy observations, we cannot do that. Indeed, this is the example for M87 observed with MAGIC telescopes. Here you can see indeed the MAGIC PSF overlapped to the radio VLA contour. This is the limitation of the angular resolution of very high energy instruments, that is of the order of 0.1 degree. So for extragalactic sources, we cannot especially resolve the sources, and for this reason we don't use images for very energy study of blazars. But blazars are very important in the very high energy sky. They are the most numerous sources in this energy range. This is the TV sky from the TEVCAT catalog, the catalog of TV sources containing 307 sources. 84 of them are blazars, that are the one marked with the red points here. You can also appreciate the superiority of blazars as TV objects by this pie chart, in which the blazars represent a large part of the TV sky. We study blazars at very high energy because between different emission mechanism. We can also study the variability at very high energy that provide us these constraints on the size of the emitting region. And the interesting fact is that at very high energy, we can measure variability timescales that are very short. For example, for this source, PKS 2155, the variability timescales was was the order of 10 minutes or something like that. And this allowed us to constrain the emitting region to 10 to the 12 centimeter, meaning sub-parsec emitting regions. So even better than what we can do with VLBI imaging. From a population point of view, we can see some features in the multi-wavelength TV energy range that are reflected in the VLBI features that we observe. Indeed, the answer to the question if all the blazars are the same, no. The answer is no. Indeed, we classify them based on the optical spectra. We divide them between flat spectrum radio quasars and BLX, where flat spectrum radio quasars show flat optical spectra with some emission lines, while for BLX we have flat optical spectra. What we observe from a multi-wavelength point of view is that FSRQ are brighter in the low energy regime, and they cannot reach the TV energy range. While for BLX, we observe the opposite situation, so less bright sources, but emitting at TV. We also classify blazars based on the synchrotron peak position. We divide them between low, intermediate, and high synchrotron peak sources. High synchrotron peak sources are always BLX, so we talk about we call them HBL, and these are the most common sources in the TV sky. From a VLBI point of view, we also observe differences between these classes. HBL show less strong superluminal motion, and they show more often limb brightening with respect to FSRQs. From population studies, we can see the differences. For example, by Lister et al. 2019, we can appreciate the difference in apparent jet speeds between different class of objects. Here we have the apparent jet speed versus the position of the synchrotron peak, and we see that BLX all show low apparent jet speeds, while for quasars we have a wider range of values for the jet speeds. And we can also check in the large archive of the Mojave program, in which we have the monitoring of hundreds of sources for about 30 years. And we can see here, this is an example of what we can find in the in this archive. We see the separation from the core of each component represented by different colors in these two plots versus time, meaning we are looking at the velocities from the slope of these data. We can find the velocity of each component, finding that the median jet speed for FSRQs are superluminal, while for HPL we have subluminal velocities, so flat plots here. And you can check by yourself, even from the Mojave data archive, that most of the FSRQ show this situation, while HBL usually show this situation. Okay, so now we can move to the examples on VHE energy and VLBI synergy for the study of blazars. I will start with this source that is TV source as J1943 that was detected by the S collaboration during a galactic plane survey. Was found by chance, and indeed there were a long-standing debate on the nature of this source because of the peculiar position in the sky. We usually don't observe blazars in the TV sky on the galactic plane. We had to, well, the solution of the problem arrived with EVN observations by Gabani first and Akiyama then. EVN observations that observed core jet morphology in this source, high brightness, temperature, and Doppler factors, and source compactness and core dominance that are all typical for blazars, while these values are not so typical for galactic sources as pulsar width nebula. These results have been confirmed by VLBI observations, multi-frequency VLBI observations that confirm these findings at different frequencies, and they also measured the core polarization and the spectral indices that are typical for blazars. In the same paper, also the Veritas collaboration presented the SED modeling for this source using a two-zone model, in which also the emission from the host galaxy was taken into account. Another interesting source was the TV source EC310 that again was for which there was a debate on the nature. From VLBI observations, they found that the parameters of the source are consistent with a radio galaxy at the borderline to a BLAC. Interesting for this source from a TV point of view is that the MAGIC collaboration found one of the shortest variability timescale ever found in TV sources of the order of 5 minutes, meaning that the condition, that the compactness of the region and the Doppler factor required for this kind of variability timescales are not consistent with what we observe at VLBI. So meaning that we are seeing here different emitting regions. From a multi-wavelength and multi-messenger point of view, both VLBI observations and SED modeling are really interesting for the study of blazars as neutrino candidates. This is the example for TXS 506 that was the famous source found in special coincidence with ice cube neutrino event in 2017. There are a lot of VLBI and multi-wavelength studies describing the jet emission and finding different models, testing different models. But here I'm showing you just two examples. The one from Lee and collaborators, they measured several parameters from the jet components. They found that the magnetic field strength decreased after the neutrino event, explaining this as a conversion of the magnetic energy density into particle energy density, meaning we have in a site of ongoing particle accelerations, and if we have protons, accelerated protons and a photon field, we can expect the emission of neutrinos. So this can be a proof of a clue for neutrino emission in this source. From a CD modeling point of view, Ceruti et al. In 2019 published these two models, hadronic models, or synchrotron model and hybrid leptohadronic model to describe the observational data and also to measure the neutrino flux and the expected detection rate for this kind of fluxes. They found that leptohadronic model better represents the observational data and also is more consistent with the neutrino event that we have measured from TXS 506. If you want to learn more on how to study Blazar as a source of neutrinos, I suggest you to have a look at this talk by Yuri Kovalev in this collection of seminars. We are also interested in the search for candidate neutrino sources. Indeed, in 2019, we started, my group and I started to collect VLBI follow-up of neutrino events, studying the ecospatial radio sources. In particular, we have published so far 4 VLBI follow-up of neutrino events, for which we have collected 10 observations of 10 radio sources, and for 2 of them we have found hints of enhanced activity around the neutrino arrival time, and that was consistent with what was observed in TXS 506 and what was expected by the Plavin, the works by Plavin et al. Published between 2020 and 2023. For PKS 1723, we have also occurred a further validation of the high state of the source after the neutrino event. Indeed, with the Telamon monitoring, they observed a high state of the source after the neutrino event that lasted a few months and started to decrease almost 1 year after the neutrino detection. We are also studying the jet component morphology and kinematics, and we are collecting new VLBI follow-up of neutrino events. We have collected 7 new of them between 2021 and 2024. This is an example for PKS 0735 that was also in a high state at the neutrino arrival time, and for which we have also a multi-wavelength description of the source by the S and Veritas collaboration that provide us with an SCD modeling, including their upper limits on the non-detection of the source during the neutrino arrival time. So the case of M87, this is not a blazar, this is a radio galaxy that is even very interesting from a TV point of view, because we usually cannot observe radio galaxies at this energy range. Indeed, The source was found in a flaring activity, was detected during a flaring activity by the S collaboration in 2005. And the flaring activity at TV energy range was found in coincidence with the optical, X-ray, and radio flare that was occurring in the HST1 region. That is a region that is separated from the central core by about 70 parsec. And so the flaring activity was found in this HST region, from which also radio observations, for which the radio observations really revealed superluminal motions that were sometimes, in some cases, connected to the very high energy variability. Another flare was detected in 2008. And this time the flare occurred in the core and not in the HST1 region from the analysis at other wavelengths. Over the following years, MT7 experienced other flaring episodes, and the position of the flare varied between core and HST1 region. Actually, now the HST1 region is decreasing its flux density in the radio observations, but the source is continuously monitored by so we have no clear conclusion about this source, but is for sure a unique and interesting case of study, both from a VLBI and very high energy point of view. And about MT7, I must mention the image of the supermassive black hole, for which we can find a nice talk by Michael Johnson in this collection of seminars. Recent VLBI results on the monitoring of this source have been published using East Asia VLBI network, including also Italian antennas. Something that we observe in several cases during TV flares are the ejection of new components. Here, an example by Lico et al., published in 2022. Here you can see the image of this source during and before and after the TV activity, and they found a new node ejection after almost 1 month after the flare at TV. You can see it also from the flux density of each component versus time. Here is the new component, the new node appearing, and you can also check the total flux density in the radio band that is in a high state in coincidence with the TV flare that was detected by Veritas. Okay, so another similar case was found in this source that was found to flare in two separate dates, separated by 2 weeks, more or less. And from the VLBI image, they found that the TV flare were associated with the entrance and the exit of a superluminal node in the recoil emission shock, in and out a recoil emission shock. That was another component in the VLBI jet. Last source, this is an FSRQ that is interesting from a TV point of view, because even also FSRQs are very rare sources in the TV sky. So the detection of this one was followed by the ejection of a new component from the VLBI image, for which the proper motion was measured and all the parameters were set and were compared to the modeling of the SED, of the broadband SED. And with this, I conclude, leaving with my take-home messages. Very high energy and VLBI techniques are different techniques, but allow us to study the most energetic sources in the universe, and in particular in the extreme states. They allow us, these techniques allow us to study very compact sources in the Blazar jets, very high energy via variability, VLBI, thanks to the very high angular resolutions. We have two very nice techniques, but they are limited due to in the very high energy case, we require specific specific condition to observe. We only observe during dark nights or and with good weather, while for VLBI we need a precise coordination of faraway antenna. But the very high energy and VLBI observations together provide us with complementary information to draw the big picture about the physics of blazars. And all these will be boosted by the CTO sensitivity and energy resolution that will allow us to constrain the high energy part of the spectrum and to distinguish between hadronic and leptonic scenarios. We will have the SKO sensitivity and VLBI and SKO plus VLBI angular resolution that will allow us the study at low frequency of these sources, even in the southern sky. But even more important for VLBI studies of blazars will be the triple band receivers that will be built on the VLBI antennas of the EVN, of some of the antennas in the EVN network that are already mounted in KVN antennas, and they will allow us to have better capabilities at high frequencies that will allow us to go closer to the central region of of these objects and to understand better these very compact and very close to the central region part. Okay, so I thank you for your attention, and I stop here.
Wow, thank you so much, Cristina, for this fascinating talk. So now it's time to open the floor to questions and comments from the audience. So please write your question either in the Q&A box here in Zoom, raise your hand, or if you are on YouTube, put them in the YouTube chat. So far I see no questions yet. I will just start off. So I don't know anything about very high energy observations. So what is, you said that, yeah, the angular resolution, so the position accuracy of this photon flux is not so, what is more or less this position accuracy?
The angular resolution is of the order of 0.1 degree, that compared to the milliard second resolution is not so good. But about the position accuracy, you can see the oh, sorry. Okay, so is not is of the order of arc seconds, I would say. So yeah.
So that's actually is very good. Okay, I see we have a question here by Benito.
Yes, great talk, Cristina. One curiosity about when you commented, especially in the last slide, about CTA, SKA, VLBI, that will happen. So both will for sure improve a lot sensitivity, resolution in both domains. Personal question is like how interesting is or how convenient is to have like simultaneous observations between both of them, or given the temporal delays on the emission, that's actually not that important. So like if you need to pick, if it would be interesting to have like strictly simultaneous, or you prefer to have CTA observations, but then within, you know, the same time ranges.
Okay.
Optical would be better.
Okay, thank you for your question. Actually, for simultaneously, we have no strict constraints about the radio observations, because we have usually delays between very high energy activity and radio activity. So we have usually flaring activity in the TV range coming before the flare in the radio band. So this is related to the fact that the emission from the very high energy is assumed to thought to come from a region that is closer to the central region. So we need some time to the radio radiation becoming transparent that occur later in time. So we don't need extremely simultaneous observations. I mean, not in. I mean, we can have some delay in the observations between the two energy bands, but yeah. So let's say for Blazars, the variability timescales are of the order in the radio band are of the order of weeks, but also months. So we have some time yeah, to do the observations after the very high energy activity.
How long does this very high energy activity last if you have a very high energy flare?
It depends on the source. Indeed, we have flaring activity that could be really on really short time scales of the order of as we have seen 5 or 10 minutes, but also lasting nights, few nights. So it depends on the source and what is the mechanism at the base of this flaring activity that is not well understood yet. But for some sources, the high state lasts even a few days. No, I wouldn't say more than that, because at very high energy we usually see a decrease in the flux very soon. But it depends on the source. For it also depends on the class of objects. For some classes we observe shorter variability timescales, and for some classes larger. Yeah.
Okay, there's a question from Uwe Bach. He says, hi, there was a plot that showed that there are about 30% of high energy sources that have unknown origin. Can you say something about how they are distributed? Are they related to our galaxy? So if that plot, is that in galactic coordinates, or are they more likely to be extragalactic?
Okay, this is the... Yeah. Here you can see the unknown sources. Sorry, yes, the pie chart is in another slide, but here I'm showing you the unknown sources are in the gray ones. So they are. I'm not sure about what kind of sources are these. For sure, there are by doing other wavelengths observations, we can infer the nature of them. But yeah, this is the distribution. I would say they are more galactic than extragalactic from this plot. I didn't check properly, but from this plot, I would say that.
Okay, thank you. Let's see, can I still ask a last question? Then maybe somebody else comes in with a better question than mine. So do you monitor the whole sky all the time in very high energies? I mean, if these flashes are so short, so you are not doing pointed observations, but you have...
No, okay, we do pointed observations, We have extremely good cameras that can get flashes lasting very short, lasting a few nanoseconds. So this is how the cameras are built. We do pointing observations and we collect as much photons as we can. There are other kind of EACT other kind of instruments that are using the same process of the Cherenkov light produced in the air or in the water, and they observe in the whole sky. So they are also not affected by the daylight, so they can observe even during the day. But for these ESCTs, we do pointed sources, pointed observations.
Okay, thank you very much, Cristina. I would like to thank also all the participants and everybody that asked questions. You can, of course, if you have later on questions, you feel free to contact Cristina. She has put kindly her email address on the first slide.
Thank you.
And with that, I hand over to Benito for some last moment announcements.
Okay, thank you very much. So just 2 quick announcements. The next seminars will happen already next year. So in the 5th of February, we will have a third room seminar from Mike Garrett talking about reinventing SETI, innovative approaches by using VLBI on the searchers. And then following that, we will have one by Tiziana Venturi in March, April of next year. So still the date will be still to be confirmed. And the last announcement that it will be something that you will see in your mailbox hopefully next week is that we are organizing the Jive VLBI school next year in September from 15th to 19th of September. So this will be a school to train participants and teach all about VLBI techniques and data reduction, and especially from EVN data. So we will send our first announcement on the date of the school, and now we are ready to prepare it. This will be a multi-hub hybrid school. So we are aiming to have participants in person at Jive in the Netherlands, and also a smaller, say, auxiliary venue in the University of Pretoria. So both sites will be connected and then will be streamed from one to another. Plus, we will facilitate some fully online participation there. So that's all for the seminar. Thank you, everyone, for joining, and thanks, Cristina, for the great talk on that. And hopefully see you next year.